this section is going to discuss the early universe. I want to give you some ideas of some of the things that have happened. So let's talk about the Quark Epic. That went on from the beginning, Big Bang, sometime in there, to 10 to the minus 6 of the second after a Big Bang. The universe was about the size of a neutron at this time, and we had freely existing quarks. Now, if you don't know what a quark is, this is the smallest particle that we've been able to measure. It's actually, we've never seen it outside of a neutron or a proton, except we're hoping to see them in the Large Hadron Collider experiments coming up. So we're going to get near energies very soon, and maybe by the time you've heard this, we'll have already done that. But they're smashing these particles. Supposedly, we're going to get to see quarks for the first time. So during the Quark Epic, they were not together in the protons or neutrons. And then from 10 to the minus 6 of a second to a second of the Big Bang, after we have the so-called Hadron era. Hadrons are neutrons and protons, and so they could start to form quarks coming together. So the quarks came together to form the protons and neutrons. Remember, protons are positively charged particles that exist inside the nucleus of an atom, and neutrons exist there also. And so we've got in the center, we've got a nucleus with protons and neutrons, and those are hadrons, then antiparticles too. And in the early Big Bang, these are going to annihilate each other. The anti-hadrons and the hadrons are going to interact. Now, you probably don't know this, but if you have a vacuum, particles are going to start to appear in that vacuum. And then it's going to be an antiparticle and a particle, and they're going to destroy each other, and you're going to have energy produced. So I know it sounds strange, but particles appear and disappear all the time in vacuums. And we'll talk more about that with quantum mechanics. But that annihilation of antiparticles with particles creates this energy, and that's what leads to the background radiation. And it also, by the way, tells us that the energy that went to form the cosmic microwave background radiation, that came from all these interactions of antiparticles and particles, and only one particle out of every billion survived. So most of the matter that was created, that existed, I should say, in the Big Bang was destroyed by these interactions. And we still don't know why this happened. Get to that a little bit later. Then we go into the Lepton Air, which is 1 to 10 seconds after the Big Bang. And in the Lepton Air, we've got pretty much, a lepton is just an electron and an anti-electron, which is called a positron. It's actually a positively charged electron. And they annihilate each other too. So all these leptons are annihilating each other, and we're left with basically only a few particles left over and a sea of photons running all over the place. And these photons then dominate the universe during the Photon Epic, which is from 10 seconds to 380,000 years after the Big Bang. And we call it the Photon Era because galaxies couldn't form during this period of time. So when we look back in time, we stop seeing galaxies because we run into this period of time when it was completely made up of just this bright photon-rich universe. And again, that's the cosmic microwave background that we see today. Now, it's kind of important what's happening here because things are going to cool down during this period of time, and we're going to see neutrons and protons starting to form the nucleus of atoms. And neutrons are not stable outside of a nucleus, and they decay rather quickly. So we're going to have them decaying faster than protons, and we're going to have protons created more than neutrons because they're slightly smaller. So there's a real preference towards protons, which means that by the time you start creating atoms in the Big Bang, from the Big Bang, you're only going to get a few elements. One of them, as you can see in this diagram, is one proton, that's hydrogen, and then a proton, if it picks up a neutron, that's deuterium. Now protons, remember, they change what kind of atom you have. So if it's a hydrogen atom, it's got 1 proton. If it's a helium atom, it has 2 protons. Lithium has 3, and so on up the scale. If you add neutrons, those are called isotopes. So if you have 1 neutron added to a hydrogen proton, you get deuterium, which is an isotope of hydrogen. And if you add 2 neutrons, you get tritium, and so on and so forth. And you can see the reactions taking place here. Sometimes we even form beryllium and lithium, but they go back and they end up as helium-4. Now, to make a long story short, everything is most matter is going to either stay as 1 proton, as hydrogen, or it's going to end up as helium-4. And we would predict from the Big Bang that we would get 75% hydrogen and 25% helium, little bit minor amounts of lithium and beryllium. And by golly, when you look out in space, you find about 75% hydrogen, and you find about 24% helium, and the rest are other atoms that are formed in another way. We'll talk about how they form in supernovae later on. The important thing to take away from this is that these things are forming and giving us a very specific amount of material in our universe. And the big question is, hey, look at us, we're in a very unique place in the universe. Not a special place, but a unique place. Some things had to happen to get all of the elements that we see around us other than hydrogen and helium. And the last question that we have to address is, why is there matter? And that is the question for the ages. And the answer is, we don't know why there's matter. The antimatter and the matter should have reacted to form energy, and we should only have energy in our space if everything's symmetric. You know, physicists love symmetry, and it seems like our physical world is all symmetry. When a crystal forms, like a snowflake, you get nice symmetry in there. Seems like almost everything has symmetry to it, and yet here we are in this real world where we've got something happening that's not symmetrical. And we're going to talk about that later, but basically the answer to that is we don't know yet. That's one of the big problems in cosmology, and that's one of the problems that they're still working on. And hopefully, if the word comes out from the world of science, I'll be the first to let you know.